This video will be on geometric transformations of complex numbers, and particularly with the case of adding complex numbers. Again, since we're thinking about the geometric transformations involved, we're going to draw an Argand diagram to represent the information that's taking place in these couple of examples and questions. My first example is going to be showing the geometric effect of adding 3 plus 1i to 1 plus 2i. So really I'm looking at 1 plus 2i plus 3 plus 1i. Now obviously if we were going to just work this out, it's really straightforward. Add the reals, you get 4, add the imaginary components, you get 3i. 4 plus 3i is the answer. But how does it look in an Argand diagram? So I'm going to start by marking in the two complex numbers in question, 1 plus 2i, which is just marked in at 1, 2, and 3 plus 1i, which is just marked in at 3, 1. And to begin with, what I'm going to do is I am going to join both of these complex numbers back to the origin. So effectively I'm drawing in their modulus. And in order to visually add them, effectively what I'm going to do is I'm going to complete the parallelogram that has been begun by the two moduli. So I'm going to draw a line that is parallel to the modulus of 1 plus 2i. And I'm going to draw a line that is parallel to the modulus of 3 plus 1i. And where these two lines cross is the result of the addition of those two complex numbers. And you can see that this point is actually the point 4, 3, which in fact is exactly what we expected from our basic addition that we did at the very beginning. So 1 and 3 was 4, and 2 and 1 was 3. So 4, 3 is the complex number 4 plus 3i. If we like, we can draw in the modulus of this new complex number, and the modulus of this new complex number is simply the diagonal of the parallelogram, joining it back to the origin 0, 0. We can also think of addition as being a translation. And I'm going to use the same example as before. So I've got 1 plus 2i, which is the point that I'm starting off with, and I want to add 3 plus 1i. And this addition operates as a translation. So I can think of it as being adding 3 to the real component. It's like I'm going 3 steps across in the positive direction on the horizontal axis. And then adding 1 to the imaginary component. So I'm moving 1 step in the positive vertical direction. And this has the result of me landing on that same solution, 4 plus 3i. If we do another addition using 2 plus 1i this time, and we add the same complex numbers before, so plus 3 plus 1i, and I'm just going to mark that in. So I've got 2 plus 1i is located here, and I want to add 3 plus 1i. Well, again, I'm going to add 3. I'm adding, so I'm going in the positive horizontal direction. And then I'm going to add 1i, so I'm going in the positive vertical direction. I can see that I land on a result of 5 plus 2i. But also when I compare the two calculations, I can see that the translation is the exact same in both cases. So when I'm adding a complex number to, such as 3 plus 1i, to another complex number, the translation will stay the same if the complex number that I'm adding is the same. These are two different methods and they each have their place. So this is useful if I have a clear Argand diagram with a scale, and perhaps if I'm trying to move a whole object made up of several points or vertices. This approach is really useful if I'm given an Argand diagram but there aren't any numbers on the axes and I'm trying to identify a point that is the result of addition of two complex numbers. Drawing in the parallelogram in that case is very useful. So here's an example of what I'm talking about. I've got 5 points on my diagram and I want to identify Z3 if Z3 is the sum of Z1 and Z2. So how would I go about doing that? Well, I have Z1 and Z2 identified. Z3 must be one of the other 3 points. So what I'm going to do to figure out which one it is I'm going to draw in that parallelogram like I spoke about before. So I start off by drawing in the two moduli. And when I complete my parallelogram, I can see that the parallelogram has this 4th vertex. So this guy must be Z3. just while we're looking at this diagram, let's see what other features we can identify or what other facts we can identify. I'm going to say, for example, that one of the other points is actually 2z3. I'm actually going to call it z5. So identify z5 if z5 is twice z3. Well, to identify this, I'm going to focus on the idea that z5 is created by multiplying z3 by a scalar. So really what that 2 is doing is it's affecting the modulus length of the complex number z3. So the first thing that I'm going to do is draw in the modulus of z3. So here's the modulus of z3. Now if z5 is twice z3, well then z5 must have a modulus that is twice as long as the modulus of z3. And I think at this point it's pretty apparent which point I'm referring to. So to be absolutely 100% certain, I'm going to put my ruler down again, and I'm simply going to measure the distance from the origin to z3 and then double it. And when I do this, it's quite clear that I land on this point here, and so this point must be z5.